And we're live. Hello, everyone, and welcome to Kraton's online event covering the highly modified asphalt technology. We really appreciate your time joining us today. It's going to be 1.5 hours, hopefully very well spent. Before I start, let me tell you about the takeaways. You will get a working knowledge of what the HiMA technology is, how it works. You'll get some examples of its implementation around the world, and hopefully you will have a good time. Now, let me introduce the panelists who will field your questions. Right next to me sits Dr. Bob Klatz. Dr. Bob Klatz is a senior scientist at Kraton. He is one of the fathers of HiMA technology. He's been involved in its development since early 2009, has managed its deployment around the world. Right next to Bob Klotz sits Mr. Gary Fitz. Mr. Gary Fitz has joined Kraton in 2018 as a market development manager. He is a professionally licensed engineer and brings decades of pavement engineering expertise. My name is Sebastian Puchalski. I've been with Kraton since 2013, worked on HiMA technology, supporting it in various roles, and I'll be hosting this event. All three of us work for Kraton, who is the original inventor of styrenic block copolymers and early pioneer of their use in asphalt applications. A few words about this event. Shortly, I'll start a video session. It will be a 2-minute. There will be first a 2-minute video explaining how this platform works that you're using right now to see us, Livestorm, explaining how to ask questions, whether you logged in from a mobile device or from a desktop computer. And right after that, we'll play the first of 3 segments of video covering the HiMA technology. It's a short video, only 10 minutes, so you will not get bored. It's very interesting. And after that, we'll pause, and we will have 15 minutes for Q&A session. So if you have questions during the video, please ask them in the question box, or ask them during the Q&A session. And we will have a total of 3 video/Q&A sessions. So it will go quite fast. Now, at the end of the event, we'll share with you a resource sheet on HiMA, so you can download it and then use it to find out more about the technology. With that, without any further ado, let me start the first video. Just bear with me a second.
The following event will be recorded, and the recording will be made available immediately after the event. The event can be viewed via web browser in a traditional desktop mode. The presentation panel is located on the left-hand side. The interactive features of the event can be accessed at all times on the right-hand side of the screen. Alternatively, the event may be attended via a mobile device. When accessing via a mobile browser, it is important to avoid accidentally closing the browsing tab. The interactive features of the event are accessible by clicking on the arrow pointing to the left. The arrow is located in the upper right-hand side corner of the screen. After accessing the interactive features, the participant can toggle back to the presentation view by clicking on the arrow pointing to the right, which is located in the upper left-hand side corner of the Interactive Features tab. Live chat feature allows for sending private message directly to Kraton. Other participants won't be able to see your message. The Questions tab is where we would like to encourage questions being asked. Other participants will be able to see the questions. However, they will only see the first name of person asking the question. During the event, we will use the pause feature a few times to gather your thoughts and opinions. It will be a simple multiple choice question. After answering it, you'll be able to see the distribution of answers. Finally, you are able to see first names of other people participating in this event by clicking on the People tab. Our daily lives depend on a reliable road infrastructure. Yet, as with many other things, we often take the roads for granted. Growing population, heavier road traffic, and increasing number and severity of extreme weather conditions resulted in stricter sustainability standards and more comprehensive greenhouse gas emission limits. These changes provide us with an opportunity to rethink the future of the paving technologies. HiMA, or highly modified asphalt, is a paving technology developed to address the needs of modern pavement infrastructure. Yet, why should you be interested in HiMA? How does it really work? And most importantly, is it a proven technology? Let's start with answering the why question. Investing in pavement infrastructure usually takes into consideration the life cycle cost of an asset. Simply put, the life cycle cost is the cost of initial construction, as well as any subsequent maintenance expenses and salvage value, all discounted to present. The HiMA technology has been shown to reduce the pavement life cycle cost. The cost reduction may be achieved in two ways. The first option is to make the initial pavement thinner, thus saving on the cost of materials. The second option is to retain the original pavement thickness and instead rely on the improved performance to extend the pavement life cycle. Sometimes, specific pavement issues take precedence over the life cycle cost consideration. HiMA excels at addressing severe rutting pavement problems by delivering extra material strength. The continuous polymer network helps to eliminate or minimize top-down and bottom-up fatigue cracking. Additionally, the HiMA-enabled asphalt mixtures may drastically eliminate or reduce a wide range of issues including reflective cracking, studded tire damage, extra heavy load damage, delayed post-construction opening time, raveling of open-graded asphalt, water damage, curb reveal or road clearance height issues, and problems related to providing sufficient pavement structural support over sensitive utilities beneath. Although reducing the life cycle cost of an asset is important, HiMA may also be beneficial to the environment. Using fewer raw materials and reducing the number of repair and maintenance cycles may have a profound impact on the carbon footprint of a pavement asset. The initial material carbon footprint of HiMA may be somewhat higher when compared to the conventional solutions. However, fewer maintenance and reconstruction operations may allow for a lower overall life cycle carbon footprint of HiMA pavements. Consequently, our society can benefit from lower long-term infrastructure spend and fewer hours lost in traffic jams due to road repair.
Welcome to a 13-step illustration that explains how Kraton's HiMA technology can help road authorities save a lot of money, more than $100,000 per mile in whole life costs in this example. The first step is having reliable data. Our example will focus on Florida, where more than 500,000 tons of hot mix asphalt using HiMA has been placed since 2017. That year, the Florida Department of Transportation, or FDOT, adopted a HiMA binder specification, designated as high polymer. FDOT routinely collects pavement performance data as part of their pavement management system and has cost data from projects readily available on their website. In addition, FDOT has sponsored several research projects evaluating HiMA applications in dense graded mixtures and in open graded friction courses. Step 2 is defining the engineering approach. FDOT's Flexible Pavement Design Manual uses the 1993 AASHTO Guide for Design of Pavement Structures, in which a pavement structural number requirement is determined that accounts for anticipated traffic, subgrade soil support conditions, and a design reliability level. The structural number concept was developed from research in conjunction with the AASHTO road test, which took place from 1958 to 1961 near Ottawa, Illinois. Simply put, as the structural number increases, the number of allowable 18,000-pound or 80 kilonewton equivalent single axle loads, or ESLs, also increases. This means that a pavement design with a larger structural number can withstand more traffic loading. The structural number for a pavement design is calculated by summing the products of thickness and structural layer coefficient for each layer. Here's an example. A 2-layer pavement which has a 2-inch thick surface layer with a layer coefficient of 0.50 and a 5-inch thick base layer with a layer coefficient of 0.20 would have a structural number of 2.00. So how does the use of HiMA technology compare to a conventional binder grade in terms of structural layer coefficient? According to FDOT's Flexible Pavement Design Manual, the recommended layer coefficient for a dense graded asphalt pavement layer using a conventional polymer modified binder grade is 0.44. One of the research projects mentioned before evaluated mixtures and full-scale pavement sections to identify the appropriate value to assign when using high polymer binder, which was 0.54. This means that the overall pavement structural number increases by 0.10 for every inch simply by replacing conventional binder with high polymer binder. The potential impacts of this could be to provide extended pavement life using the same layer thicknesses, or to reduce the pavement layer thicknesses to provide the same structural number. So far we've discussed the pavement engineering approach. Now let's look at an example roadway section. We selected an undivided urban arterial which includes the following. On each side there is a 4-foot wide bike lane with 2 11-foot wide travel lanes. In the middle there's a 12-foot wide turn lane. The pavement design criteria for this road are as follows. The traffic projection estimates 10 million easels over a 20-year design period. The design reliability level is 90%, and the pavement will be built over a subgrade having a resilient modulus of 10,000 psi, or about 69 megapascals. According to the FDOT Flexible Pavement Design Manual, these conditions would require a structural number of 4.50. This would be satisfied by a pavement structure consisting of a 5-inch or about 12.5 centimeters of hot mix asphalt using a conventional binder, placed over 10 inches or 25 centimeters of Florida lime rock base, all of this over 12 inches or about 30 centimeters of a stabilized subgrade. Using the higher layer coefficient recommended when using HiMA, replacing 3 inches of the structure, or about 7.5 centimeters of hot mix asphalt using conventional binder with HiMA, increases the structural number by 0.30. For the assumed design conditions, this would increase the number of allowable easels by almost 6 million while maintaining the same thickness. Another way to look at this is that this would extend the anticipated 20-year pavement design to almost 30 years. The extended performance life is an important consideration for agencies and those designing pavement structures to take into account. According to FDOT's Pavement Type Selection Manual, flexible pavement structures using conventional binders require rehabilitation consisting of milling and resurfacing every 16 years. Based on the improved structural performance of HiMA mixtures, this rehabilitation cycle could be conservatively extended from 16 to 22 years. This can significantly impact the results of an economic analysis of a project. Let's consider the costs associated with building and rehabilitating an urban arterial route. Using published FDOT cost estimates for this type of roadway, the average cost for new construction using conventional materials is around $5.8 million US. Milling and resurfacing as prescribed in the FDOT publications is estimated at $1.2 million US. In both cases, the cost estimates include everything: mobilization, traffic control, pavement marking, signs, etc., more than just pavement materials. FDOT publishes average unit low bid prices for contracts they've awarded. From this information, the cost of mixtures using HiMA can be estimated and used to adjust the total project cost estimates mentioned before. Using this information, the differences in total cost of new construction and rehabilitation using HiMA were 5% and 17% respectively, assuming a cost difference of $25 per short ton of asphalt mix. The time value of money, in the form of a discount rate, must be considered when performing an economic analysis. An analysis period must also be defined, which extends beyond at least one rehabilitation cycle. The U.S. Federal Highway Administration's Real Cost 2.5 software is a tool used by many agencies to perform this type of analysis. FDOT guidelines use a 3.5% discount rate over a 40-year analysis period. Now we have the information we need to estimate life cycle cost for HiMA versus conventional binders for this example. To recap, for each alternative, we have a cost of building and rehabilitating the pavement, pavement rehabilitation schedules, an analysis period, and an assigned discount rate. The salvage value is calculated to account for the remaining life of each pavement alternative at the end of the 40-year analysis period, which is also discounted to a present value. As mentioned before, the real cost software was used to calculate the net present value, or in other words, the life cycle cost for each alternative. Assuming a conservative cost difference of $25 per short ton, replacing 3 inches of hot mix using a conventional binder grade with HiMA reduced the life cycle cost by $110,000 per mile. In order for a conventional binder to be cost effective, the cost difference in the mixtures would have to exceed $34 per ton. For 10 miles of an urban arterial roadway, this would amount to over $1 million in savings over the 40-year analysis period. Similar results were seen in analyses of rural arterials and limited access highways under Florida conditions.
Okay, so we are back to the event. I hope you enjoyed the video. I hope you have. We've seen already a few questions coming in. I'm just navigating to see if there's any new ones. If you do have questions, please ask them. Our panel is here to answer them. I will ask some questions from my end. The first question I wanted to ask is, has HiMA been used in combination with wrap mixtures? And if so, what's been the performance of HiMA?
Gary? Okay. Yes, that's the easy answer to that question. And let me cite some examples on that. Probably the best examples come from the National Center for Asphalt Technology test track at Auburn, or Opelika, Alabama, outside of Auburn, which has been in operation since around 2000. Most recently, I guess probably the best examples would be there was in one of the experiments, there was a high modulus mixture experiment where they used 35% wrap with highly modified asphalt that performed very well. And then more recently, there was the cracking group experiment, which included highly modified asphalt in the base course. And this was for all 6 of those test sections. And what they tried to do was to use this as a means of generating or resulting in top-down cracking, but without cracking coming from the lower layer. So they used highly modified asphalt to have a thin deflecting pavement section that would result in that. Those sections all had around just less than 20% wrap in them. And one of the sections there, S6, in that cracking group experiment had highly modified asphalt in the surface course as well, which had about the same amount of wrap in it. By the way, that test section performed extremely well with practically no cracking after 20 million ESCL.
Okay, thank you. Actually, some new questions came in. Question, is there any test done in cold weather region? I suppose, has HiMA been used in cold weather? I think, Bob, you're the expert in this.
Well, I will answer there in that Alaska, just as an example, has started using it extensively on major city streets in Anchorage, largely because they've been able to formulate it to help mitigate studded tire damage. And in fact, so the PG grade that has been used in Alaska is a PG 64-40. And in fact, a recent project that was paved in Fairbanks, where they really want to mitigate thermal cracking but still get adequate rutting resistance, they paved with a PG -46. So yes, indeed, absolutely, it works very well in cold climates. And just as a general observation, the modified asphalt has a profound effect on intermediate temperature cracking and high temperature performance. It has only a modest impact on thermal cracking. So as a general guideline, the base PG LTPP bind low temperature grade is typically going to be the base asphalt low temperature grade that you'd start with.
Okay, thank you, Bob. And by the way, just comment, we will have several case studies, and Alaska will be one of the case studies covered in the 3rd segment. Another question, does this material need any special equipment or operation?
Gary? Not really. The way that this material is is handled, let's say if we go back to the location where the binder is being produced, the same types of facilities used for producing typical or conventional polymer modified grades such as PG76-22 are used for producing HiMA. When you move from that on out to the hot mix plant and then paving operations, again, storage tanks would be the same types of storage tanks, or the same ones that are used for conventional materials, and really no difference in paving and compaction operations, aside from something at the very tail end of the compaction operation. And I don't know if we'll be getting into that later, but I can describe that briefly. Highly modified asphalt will stiffen at a higher temperature than other binder grades. Typically, and from what research that we have done here at our laboratory in Houston, is we've seen about a 25-degree increase in the cessation temperature that you would have for when using HiMA. And so consequently, that's something that needs to be accounted for during construction. But as far as whether that's been an issue in Florida, where there's probably been more work done with HiMA than anywhere else in the United States, there was an evaluation of projects looking at the pay adjustment factors for in-place density. And what they found was that on 16 of 17 projects, the average pay adjustment was a bonus for those projects for in-place density. And on the one project that there was not, it was discontinuous paving operation, which would have been a problem no matter what binder you were using. So generally speaking, this is going to handle like any other polymer modified binder, not significantly different.
Yeah, and the volumes that were paved speak to it. There was no special need for equipment. Maybe as a follow-up question from the same person, could you refer, I think you would be good for that, Gary, could you refer where in Florida HiMA has been used? And maybe there's been a lot of places, so select few.
It's been used all over the state. I don't know if it's been used in every district. There are 7 districts plus the Turnpike District, as they call it, which extends over much of the peninsula there. Probably the most that's been used has been up in the Panhandle, where they actually get a little bit higher temperatures, but you also have crushed gravel aggregates that are being used. They've had more of a history of rutting in that area. And typically what we've seen there is that they will tip more often than not, they'll be using HiMA in areas where they've had a history of rutting or cracking or other types of problems, which they feel like they can't deal with in any other way. And there's been more of that in the Panhandle than elsewhere for several reasons.
And we'll have a case study in part 3 of the video that highlights its use. Question from Mr. Torres Verdin. Have you measured, and this is a kind of technical question, have you measured pavement deflection in Florida and compared back calculated AC moduli of HiMA versus conventional binder?
Thank you for the question, Victor, my friend. We have not measured that in Florida. However, I think, as mentioned before, there's been extensive experience at NCAT doing that, and there has been a lot of deflection testing there, and that's been looked at in the laboratory as well, doing modulus testing there. And there's plenty of reports that you can find available on the NCAT website where you can see that information.
I'll add to that too. Again, if you're familiar with NCAT, they do extensive deflection testing, extensive FWD analysis, and generally what you see is that the modulus of highly modified asphalt is higher than conventional PMA, maybe by a factor of 2. So to distinguish that from some of these very high modulus materials, such as EME, it does not have such a high modulus as the very stiff, literally air-blown binders, but a lot of its performance comes not so much from its stiffness, but from its resilience and resistance to cracking.
And I think just to add a little bit to that, as we all know, stiffness or modulus, when we're looking at asphalt mixtures, depends on temperature as well. And one thing that we see with highly modified asphalt mixtures is that the material is less temperature sensitive than other materials would be. And that's the effect of the polymer and the high polymer content.
One caveat from that in introducing HiMA technology and initiating projects is it's a challenge in pavement design because the performance is so much superior than you would expect just from the modulus of the material. So it makes it challenging to use design tools like AASHTO 3.1 that are dominantly controlled by the pavement design is dominantly controlled by the modulus.
Thank you, Bob. Thank you, Gary. I just want to tell you, I'm looking at the questions. We have a lot of questions coming in. We're at 8 minutes of 15, so we have a few minutes left. We'll get through most, or not most, but as many as we can. But I promise that we will answer them either during or after the event. Quick question from Amina. What is the polymer percentage used in HiMA binder? The next segment will explain all about that. Quick answer, about 7.5%. Next question from Mr. Riyad Islam. Does HiMA perform better in fatigue resistance since we are reducing asphalt thickness? I think that's an interesting question. So we're saying we were reducing asphalt thickness, but at the same time, we're saying we're improving fatigue performance. Could you elaborate on that?
So let me give a simple answer on that in that from the work that has been done at NCAT, they've estimated that, I'll go back and talk in terms of endurance limit. So how much tolerance, fatigue, how much strain can the pavement tolerate? From the work that NCAT did, they estimated that the endurance limit, the amount of strain that the pavement can tolerate at the bottom is at least 2, maybe 3 times as high as the endurance limit for conventional unmodified asphalt and even regular modified asphalt. So that means that yes, you can reduce the thickness of the pavement and still have as good or superior bottom-up fatigue cracking resistance.
Yeah, to add to that as well, and going back to NCAT, if you look at the performance of the initial test sections that were built using highly modified asphalt at NCAT, there was a comparison between a 7-inch pavement and a 5 3/4-inch thick pavement, which had HiMA in all the layers in it. And what they found from that was that with the thinner pavement structure using highly modified asphalt, they had superior performance both in rutting and in much less cracking in that. In fact, I don't think there was any evidence of fatigue cracking from the bottom up in that.
There was zero bottom-up fatigue cracking in any of the cores that they checked.
And consequently, they were concluding that that was a perpetual pavement section. Now, remember at NCAT, you have a very sound foundation that you were building on for those test sections. So you wouldn't say that you can take and apply that thin of a pavement section just anywhere and everywhere. And of course, the loads matter as well. But as far as whether you get better performance from a fatigue standpoint with highly modified asphalt, I think the answer is clearly yes.
Thank you. I think the next question is quite interesting. It will be partially addressed in the next video segment, and it deals with specifications, but maybe we can comment just with our experience. The question goes, what is the best way to specify HiMA to make sure you get the product you want?
Let's start out with what specification system works best. We're lucky being in the United States because the PG specification system really helps with novel materials versus penetration, viscosity grading. So that helps a lot. The MSCR specification, M332, is the best tool that we're aware of for specifying. And we've used that quite successfully with almost no modifications. So like I said, the low temperature grade is just the low temperature grade from LTPP bind. The high temperature grade is really extreme. We actually cheat a little bit in grade bump simply so we can get numbers that are measurable with the MSCR test. So example, for a 64 minus 22 climate, a typical spec would be 76E minus 22, plus that you'd be measuring the JNR, the limit would be 0.1 instead of 0.5 with a 90% recovery. And that's been really very satisfactory for us.
Yeah, those criteria are much more severe than the extreme criteria that you see in AASHTO M332 that are specified. And as far as what one might do from a QC standpoint and looking at what materials are received and how you would test that, probably the easiest way to do that is to look at the MSCR recovery at the elevated temperature. So if it's being specified at 76 degrees C, then testing for MSCR recovery at that will be a very quick and easy test to assure that you're getting what you specified.
Yeah, I absolutely agree. It's a quick test, and we'll have a video on that in just in a moment. So thank you for the question. The next question, could you please talk about, I think it's a good one, could you please talk about use of HiMA in pavement preservation and its effectiveness in increasing serviceability or delaying rehabilitation needs? And we have 2 minutes.
Okay. Let me give two very quick, I'll try to be fast and give a couple of answers. First and foremost, highly modified asphalt is one of the technologies being promoted by the Federal Highway Administration through the EDC 6 TOPS initiative, Targeted Overlay Pavement Solutions, for exactly that purpose. Thin overlays as a somewhere between a rehabilitation and a preservation technique. Also, it works very, very well in applications like microsurfacing, slurry seal, to give much improved resistance to, it will not completely mitigate bottom of cracking, but it will minimize it, and it will very much help surface abrasion and scuffing.
Thank you, Bob. Maybe as a follow-up question, 1 minute left, so shortly, aside from structural benefits, any insights into environmental aging performance of HiMA binder compared to conventional non-modified binders, as such aspects should also be considered in rehab evaluations?
Don't have very much time to answer that before we move into the next portion, but very quickly, the Florida DOT had Texas A&M's Transportation Institute do a study looking at open graded friction coarse mixtures, and they did extensive laboratory aging on those. And the aging characteristics, or the aged characteristics, of a highly modified asphalt were much better than those of the PG76-22 is being compared with, and consequently would have been much better than conventional unmodified material.
Thank you, Gary.
Just to add one point on that, this is very much true for highly modified asphalt. It's generally true for SBS modified asphalt in general, that studies that have been done on 20-year-old pavements where there's been side-by-side unmodified and modified, the modification characteristics are improved, so there is still resilience in the material. It has better low temperature properties. So even 20 years later down the road, the modified asphalt has better properties than unmodified.
Thank you. With that, we'll pause the video and move on to the next segment.
Let's now discuss how HiMA enables the mentioned benefits. HiMA should really be understood on two distinct levels, the asphalt mixture level and the asphalt binder level. This is a schematic illustration of a conventional SBS polymer. The solid blocks on both ends allow the polymers to assemble together in asphalt binder. They also give the PMA its strength. The rubber segment in the middle makes the PMA elastic and resilient to cracking. The durability of the polymer network grows as the dosage of the polymer in asphalt binder increases. In this demo, the polymer modified asphalt samples containing different SBS dosages were subject to a creep test at a room temperature. Increasing the polymer concentration visibly led to significant gains in the material strength. This phenomenon is often characterized using an S-curve analogy. In the lower part of the S-curve, the material acts as a traditional polymer modified asphalt. However, as the polymer concentration increases to approximately 7 to 8% SBS, the material reaches the upper plateau of the curve. In that region, the material starts acting like an elastic band. Reaching the continuous polymer network effect, achieved at a typical SBS concentration of 7 to 8%, is very difficult using the conventional SBS polymers. The very high material viscosity prohibits normal operations of the PMA and asphalt mix plants. Additionally, the asphalt mixture workability becomes very challenging. To enable the high levels of modification in the paving applications, Kraton invented a new type of SBS polymer. The unique design enabled faster dissolution time in asphalt binder, enhanced cross-linking capabilities, and ultimately a lower viscosity of the polymer modified asphalt. The unique nature of Kraton's polymer enables creating a dense continuous network necessary to achieve a step change in material performance. This simple demonstration visualizes the strength and the elasticity of asphalt binder with a continuous polymer network, the kind achievable with the HiMA technology. Although enabled by Kraton's polymers, the HiMA technology itself is not proprietary. Numerous construction material companies implemented HiMA into their product offering. Additionally, a growing number of public agencies used HiMA to improve their infrastructure while utilizing the existing specification frameworks. However, as with any novel technology, the conventional test limits are often inadequate to properly capture the HiMA PMA unique characteristics. Polymer network is at the core of the HiMA technology. MSCR, or Multiple Stress Creep Recovery Test, is a convenient surrogate tool for evaluating the polymer network quality in asphalt binder. Dynamic shear rheometers used to perform the test are sensitive to even small differences in the material performance. HiMA PMAs are typically tested at 76 degrees Celsius and a 3.2 kilopascal stress level, with a specified minimum 90% recovery. At these conditions, only the PMAs with a continuous and robust polymer network can pass the limit. The HiMA PMAs are also specified with a maximum viscosity limit, yielding a material that balances both the material performance and workability. What happens at the asphalt binder nanoscale has a set of very profound effects on the asphalt mixture performance. Asphalt mixture design is an act of balancing the rutting and the fatigue resistance. Improving one parameter typically comes at the cost of deteriorating the other. The concept of the balance mix design may help to reach an appropriate balance. Nevertheless, making incremental adjustments to the aggregate gradation or the asphalt binder content has its limits, especially when the pavement structure must be thin or is subject to a heavy traffic. Conventional polymer modified asphalt offers an excellent but limited solution to this problem. The HiMA technology offers a more powerful solution to easily address both fundamental distresses at the same time. To illustrate the unique capabilities of the HiMA technology, we have prepared a set of demonstrations utilizing small asphalt mastic specimens. The specimens were made with 90% washed sand and 10% asphalt binder by weight. Each demonstration features 3 specimens. The first made with a conventional paving asphalt binder, the second utilizing 3.5% SBS modified asphalt binder, and the third made with a highly modified asphalt binder. The first demo was conducted in an environmental chamber at 140 degrees Fahrenheit. Each specimen was loaded with 100-gram weight. Despite the same aggregate and binder content in mastic, the HiMA's continuous polymer network provided a visible improvement in terms of the permanent deformation resistance. At the intermediate temperature, where the load-induced fatigue cracking usually occurs, the HiMA polymer network allows asphalt to reliably recover after flexing. This helps minimizing the crack formation and propagation. The third demonstration concerns the durability of pavements built with the HiMA technology. A golf ball falling from a set height will impact each of the 3 specimens. Both the unmodified and the conventional PMA specimens did not survive the impact. The ability of HiMA to withstand the impact highlights the unique capabilities of the continuous polymer network. As compared to the unmodified asphalt binders, the conventional PMAs allow for a step change improvement to asphalt rutting and fatigue performance. HiMA, with its fully continuous polymer network, take these improvements to the next level. Any comprehensive HiMA technology coverage requires addressing the aspects of asphalt mixture production, paving, and opening to the traffic. The low viscosity nature of the HiMA technology allows for asphalt mixture production process that is similar to that of the conventional PMA mixtures. Additionally, it is possible to produce HiMA mixtures with significant quantities of reclaimed asphalt. HiMA asphalt is relatively easy to handle. The conventional warm mix asphalt technologies can be used to further improve the mixture workability and reduce the production and paving temperatures. After placement and compaction, HiMA mixtures reach the conventional asphalt mixture stiffness at a relatively higher temperature. This characteristic may allow a faster opening to the traffic without risking premature pavement deformation.
Hello, everyone. We're back. First of all, I want to thank you for all the questions you've been asking. There's many of them. Certainly, we will not be able to answer all of them live, but I promise we will answer all of them eventually. Let me go back to the questions to start asking our panel. Okay, so first question that came as we were talking, does producing HiMA require any homogenization time period after the binder is just prepared?
So I'll give a very quick answer on that PMA in general requires some sort of compatibilization technology to minimize separation. That's also true with HiMA, and it's true to about the same extent with conventional SBS modified asphalt. The technologies that are used to phase stabilize conventional PMA work just fine with highly modified asphalt.
Thank you, Bob. Moving on, how about the mixing and compaction temperature for HiMA?
First and foremost, do not use viscosity charts. Those do not work. They don't work with conventional PMA, and they're even worse for highly modified. As a general rule, this is something that you should talk to about the producer of the modified asphalt, the highly modified asphalt, and we are also able to get good advice on that. As a general rule of thumb, you do not need temperatures very much in excess with what you would use with conventional modified asphalt, and that particularly applies to construction. So generally, the temperature that you want behind the paver for 7622 is about the same as what you'd want behind 76E minus 22.
Yeah, and to add a little bit to that, remember that mixing and compaction temperatures that are identified for laboratory work, for molding specimens and compacting them, are different. They're not the same thing as what you have in the field for paving and compaction. So let's make sure that that's clear. But as Bob said, as we look at those mixing and compaction temperatures, traditionally the equiviscous temperatures that are used, that does not work with modified binders, and especially does not work for this. Typical numbers that we've seen used are around 170 degrees Celsius, 340 Fahrenheit for a mixing temperature, and then for compaction around 150 Celsius, around 300 degrees Fahrenheit, especially when using gyratory compaction.
So Bob, Gary, a follow-up question. One of the viewers asked about the use of warm mix additives in conjunction with HiMA. Could you comment on that and perhaps the compaction?
Okay, that's routinely done. And what that doesn't really affect so much is what's going on at the asphalt plant. And that's pretty typical with what we see with other with other modified binders as well, is that you don't see the effect of warm mix additives so much in mixed production temperature, at least not, it's been done before, but that's not typical. Usually what that's being used for is for, number one, to improve the workability of the mixture, especially as it cools. And secondly, many of these additives also function as liquid anti-strips as well and improve the adhesion between the binder and the aggregates. As far as the effect that it has on highly modified asphalt, again, it's being used. Several different types of the chemical warm mix additives in particular have been used and used very successfully with highly modified asphalts. I'm sure that the foaming applications in the plant that are often used have been used with HiMA. Whether that makes a difference or not, it probably doesn't based on some work that I have seen done, but it doesn't hurt anything either. Do you have anything else you want to add to that, Bob?
Basically, that's been our experience. One of the very first commercial HiMA projects that we did in Oklahoma, they used foaming. It worked very well. They were quite happy with the result.
Thank you. Another good question. The viewer is asking, how do you differentiate between, I think it's a very pertinent question, right? How do you differentiate between strength and stiffness for the low temperatures when using highly modified asphalt? And maybe I can expand on that question. How do you, in general, differentiate HiMA from a mix that is stiff? Because both are higher strength or higher stiffness.
It's a matter of stiffness is easy to measure. Strength is not so easy to measure. That's basically they're not the same thing. So the stiffness of the material is just as modulus. The strength of the material is how susceptible it is to strain and stress without deformation, and worse, without damage. You get a significant increase in stiffness, maybe a factor as much as a factor of 2 at high temperature. You get a substantial increase in strength of the material and resistance to damage. So that's the primary benefit that you get from highly modified asphalt. It's not going to deflect yet less. It'll deflect a little bit less, but the main thing is it tolerates that deflection far better than even conventional modified asphalt.
Yeah, the stiffness difference, and again, stiffness is the stress over strain, or the ratio of stress over to strain, is going to be mostly affected at high temperatures or at low frequencies. If you look at high frequencies and low temperatures, you won't see that big of a difference. That's mostly controlled, as we described before, by the bitumen that you are modifying. But one thing that we will see there, and this is something that can probably be distinguished best by doing mixture testing, is that you have a stronger, tougher material that's more resistant to cracking, or that can stand more deformation before cracking at low temperatures when using the highly modified asphalt than you do with other binders. And so as far as having a single answer, there's no such thing, but there's a lot of test results you can look back at that have been published by NCAT, obviously. And I think that's something that you can look at on a mixture to mixture basis using tests like a thermal stress restrained specimen test. That's easier said than TSRSC is the easiest way to say that. But those types of tests that are, or the DCT test, those types of tests that are looking at the qualities of the mixture at low temperatures would be the best way to designate that.
Yeah.
One more comment on permanent deformation and rutting, and just want to stress what these specifications do. So a 64E minus 22, which would be a high performance binder, for highly modified, instead of a 0.5, we would have a JNR of 0.1. Plus, we're going to be testing it at 2 levels higher in temperature, which is about a factor of 2 each. So in terms of just actual values, a highly modified binder is going to have, just for the binder property, 20 times the permanent deformation resistance of an E grade from a conventional 7622, something like that. That characteristic allows you to do all kinds of interesting things way beyond the scope of this talk today, but we'd love to talk to you about it. It gives you all kinds of tools that you can use in terms of balanced mix design to adjust binder content, to adjust mixture design, to balance rutting resistance and cracking resistance. Basically, you don't have to worry about rutting resistance, and you can adjust the binder content and gradation to any degree of fatigue resistance that you need.
Yeah, I think the important thing to remember here is that when we distinguish between conventional polymer modified grades and highly modified, is besides looking at test results or describing MSCR criteria and so on, the important thing that we're doing here is we're converting this from being a polymer modified asphalt or bitumen, where we've taken asphalt binder and improved its qualities using SBS, to something which is really performing or acting more like a asphalt extended polymer, to where it's the polymer qualities that are controlling how this material behaves and consequently results in a stronger, more elastic material.
I'll just pull this right now. So this is just an example.
That was his cue.
This is just an example, and I'll just stretch this and we can go on, and then we'll look at it again in just a minute. So this is something.
All right, I make sure that it's viewable. Yeah.
Ouch!
Hold it up.
So here we go. I'm just going to let it go. Okay, let's go on, and we'll come back and look at that in a minute.
Okay, let's pay attention to both the bar and the questions. Thank you for answering. By the way, for those of you, for all of you actually, whether you're operating on the PG or empirical specification system, we have specifications for HiMA written down for both, and they are available on our website, and they will be available at the resource document at the end.
We have suggested criteria for those specifications.
So let me ask the next question, very practical. Is there any product from HiMA which can be used very thin, and the indication is 30 to 50 millimeters, overlay over concrete pavement?
Let's break these things into two different parts. As far as very thin applications, yes, indeed. It was mentioned before about HiMA being used or being emulsified and used in that form in microsurfacing and slurry seals. And there are plenty of examples of that within the United States that we can describe, but also in what we would call thin bonded friction courses. A number of states have specifications which require the use of what we would call a spray paver, where a membrane is put down in front of immediately in front of the screed, and then the mix is placed directly on that. HiMA can be used in that emulsion membrane as well as in the mixture that's placed over that, which would be a very thin, very crack resistant layer that you would have. Now let's talk about doing that over concrete. My own personal preference would be to use that type of application when you're paving over concrete. But one issue with concrete there's a couple things that go on there that you have to consider, is that if the concrete pavement is unstable, and that is if you see it moving at the joints or at the cracks, if there's vertical movement especially, then it doesn't matter what you put over there, it's going to somehow reflect on up through. So remember, you're only dealing with the symptom, not the disease. If it needs stitches rather than a Band-Aid, then you need to deal with that, or you need to do something such as a fractured slab technology in order to stabilize the movement on that concrete pavement. But if you have a concrete pavement which is in good condition, and let's say, for example, a continuously reinforced concrete pavement to which there's limited or no punch outs and so on, if any spalls can be repaired on that and then it can be surfaced with something like that, it can perform very well as a preservative type treatment on that and provide functional rehabilitation. In other words, improve the ride quality and the other surface characteristics that you can get from asphalt that you can't get from concrete.
One more quick addition before we move on. So this is exactly what was done in New York City on First Avenue, 50 blocks of First Avenue. They milled out 1 inch, they replaced 1.5 inches, and this is over very old, very poor condition concrete that was the worst distresses were mitigated on that, and that was paved in 2013, and the pavement is still in excellent condition today.
Yeah, and you can go see that on the New York City DOT website, where they show where you can get an indication of how they rate the pavement condition for that section of streets there in Manhattan on First Avenue. Yeah, that was a jointed reinforced concrete pavement, and a lot of the distress on that was caused by utility companies. But again, they went in, repaired that, and the pavement still remains in excellent shape. The last time I saw it, though, they were letting the utility companies back in there, so they were kind of fouling some things up there too. But you can't do anything about that.
Yeah, for sure. And you can read about this case study on our website. Maybe before we move on, I just wanted to point to the bar. It has shrunk.
So there's a demonstration, 0 permanent deformation.
But
works.
Also the definition of elasticity is being able to recover its original dimensions, and there was a good example of that.
So let me ask you, let me switch a little bit the topic from technical to cost. A great question from Mr. Jan. Would it be cost effective to use HiMA on low volume roads?
Interesting question. You know, when you, in the piece that you saw earlier that was doing life cycle cost analysis, we were able to access numbers from the Florida DOT website where there was extensive experience. And so you have a pretty good gauge in terms of what the costs were and also how the costs of mixtures using highly modified asphalt are different than those from using other binder grades. So without knowing the location and knowing those details, it's impossible to answer that. But the main thing that you gain from highly modified asphalt is you get an extended service life. And that's something that needs to be accounted for as you're looking at this and as you're pulling things back to present value. Another thing that's important to point out when you're looking at doing a life cycle cost analysis, whether you're talking about HiMA or other types of things, is that remember that the paving operation is not the only thing that happens during construction. You're going to be mobilizing, you have pavement markings, you have signs, you have other types of things that go on with construction projects. And the further you can delay those, the more discounted those are when you're looking at doing a present worth comparison. So the answer is there will be conditions where it is cost effective, then there's probably going to be some where it isn't, but you need to analyze that, but take those things into account that I was just describing.
Maybe I can add to it. In Poland, HiMA has been used by the regional, we can call regional district for local roads or regional roads. And they have found HiMA to be cost effective in a wide variety of types of roads. So in other words, they are looking at HiMA not necessarily as a technology to address certain rotting or fatigue performance issues, but rather as a cost saving technology.
Yeah. And as you were mentioning that, I thought about another example or series of examples that I saw a couple of months ago when I was up looking at some projects with my friend Larry Patrick with the Oklahoma Asphalt Pavement Association. In Oklahoma, one of the prevalent uses of HiMA, or 76E-28 as they refer to it, is in a mixture they call a rich intermediate layer, which is something that is being paved on top of an existing pavement, which has been milled in most cases, but not all, but where there are cracks. And what this layer is there for is to control or to slow down the reflection of those cracks through the surface. Interestingly, when we went out and looked at projects, that several of those projects were actually county roads. There was one out just west of Enid, Oklahoma that we looked at, which is owned by the county, where they used HiMA in the rich intermediate layer in order to prevent or delay reflection crackings coming up from the underlying pavement. And they used just an unmodified binder in the surface course on top of that. And so when we look at low volume roads and that sort of thing, that's probably a good example, or the best example I can think of where it's actually being used in the United States and where it's apparently very cost effective for them.
Bob, maybe you can comment. One of Kraton's plants where we produce SBS is in Belpre, Ohio. Mm-hmm. And there we have a road that was paved with HiMA.
And that was actually, the test track at NCAP, that was the second pavement with highly modified asphalt that was ever put down in the U.S. The first was around city streets in around our plant in Ohio. A lot of it's a city. They used river gravel. So not very sophisticated pavement design, mixture design. And those pavements are still in place and they still look way better than a lot of the other streets around the area. So there can be cases where it can be cost effective long term.
Yes. And we encourage you certainly to look into evaluating your pavements for these cases. We've arrived at 15 minutes, so we'll pause again and play you the third video, which deals with a lot of examples where HiMA was used around the world and more specifically in the United States. So bear with us.
So far, it's been explained how and why to use HiMA technology. The third question, perhaps the most pertinent, has HiMA been shown to work in actual pavements? To answer this last question, we start back in 2009, when the first HiMA test section was built at the National Center
for asphalt technology in Opelika, Alabama. The Kraton HiMA test section was constructed along with a group of conventional PMA reference sections. This study aimed to demonstrate that it was possible to make asphalt pavements thinner and more resistant to both cracking and permanent deformation all at the same time. All sections, conventional PMA and HiMA, were subjected to 20 million equivalent single axle loads over a course of 5 years. Despite being 18% thinner than the conventional sections, HiMA resulted in 70% reduction in rutting and no bottom-up fatigue cracking, while the control conventional section developed 18% surface area cracking. Here are a number of commercial project examples. In 2010, at the Port of Napier in New Zealand, HiMA was used to successfully address severe rutting issues stemming from extra heavy container handling equipment. In 2012, HiMA emulsion was substituted for latex modified asphalt emulsion in microsurfacing of 4.5 lane miles of local streets in Dallas. That same year, Oklahoma Department of Transportation used HiMA to address severe rutting issues related to poor soil conditions on Interstate 40. Also in 2012, HiMA binder was used to address a similar rutting issue on US 231 in Troy, Alabama. In New York City, HiMA was used on 53 blocks of Manhattan's First Avenue. The project was complicated by sensitive infrastructure and numerous penetrations, yet construction went very smoothly. The Viracopos Airport in Brazil benefited from HiMA's superior load-bearing capability, allowing for substantial reduction of the taxiway wearing course thickness. In the Brazilian state of Santa Catarina, HiMA helped avoid full pavement reconstruction. Instead, the top 2 layers were replaced with HiMA at reduced cost. On US 290 in Midway, Florida, heavy traffic next to a large truck stop was causing severe rutting issues. A HiMA friction course helped to address the problem in a simple and quick manner. The Regional Road Administration in Katowice, Poland, successfully piloted HiMA, searching for a more sustainable and affordable pavement technology. The MS3 bridge in Ostróda, Poland, featured a unique use of HiMA binder in mastic asphalt bridge deck application. In Anchorage, Alaska, HiMA helps address the rutting problems caused by studded tires, which are commonly used in winter. A Tampa, Florida field study conducted by the Florida Department of Transportation has shown that HiMA was successful in reducing the occurrence of concrete joint reflective cracks and rutting in asphalt overlays. In 2018, HiMA technology was used on a tollway in Rajasthan, India, to protect the asset from damage related to extremely heavy traffic and occasional flooding. In 2018, in Prague, a damaged runway was repaved with HiMA while the airport was in operation. As of late 2020, all of the above-mentioned pavement projects continue to provide excellent performance. A number of states have developed specifications for HiMA binders. These vary from provisional specs for a first-time trial to full specifications with 6-figure tonnage bid per year. The interesting point is the diverse applications that vary from state to state. Oklahoma has used HiMA as a rich intermediate layer to prevent bottom-up cracking and in structural layers to solve rutting problems. Florida uses HiMA for overlays in high-stress areas. Virginia uses HiMA in their SMA mixes to minimize reflective cracking. New Jersey and New York use it for waterproof bridge decking. Alaska uses it to mitigate studded tire damage. Whether solving a particular performance-related problem or lowering the life cycle cost, HiMA technology provides a unique value proposition in a broad variety of pavement assets. With well over 5 million tons paved and in use around the world, HiMA is not a fad, rather it is a proven and reliable technology. It is crucial to recognize that the progress achieved by HiMA would not be possible without the active adoption and participation in this technology by innovative material and construction companies, forward-looking road owners,
public transportation agencies, as well as academic institutions, all of whom had unique and important impact on HiMA technology. If you think that HiMA technology could benefit your business or improve your pavement assets value, but are not sure where to start, you're in the right place. In addition to supplying specialty SBS polymers for HiMA technology, Kraton provides comprehensive support for parties interested in adopting HiMA. Kraton's Asphalt Innovation Centers located in Amsterdam, Houston, and Mumbai provide HiMA PMA formulation and testing assistance. Kraton's commercial and technical teams possess experience and knowledge helpful in tailoring HiMA technology to very specific project needs. Thank you for your attention, and please make sure to get in touch with us.
And we're back live. Welcome. Thank you for sticking with us until this time. We have quite a few more questions to answer, so let's dive right into it. First question. Pavement sustainability will become increasingly important. Can you possibly comment on how HiMA can impact the sustainability aspects from a total life cycle standpoint?
Total life cycle is exactly what you need to talk about with sustainability, with modifieds versus unmodified asphalts. In fact, that's something that the Asphalt Institute has worked on, and what NAP is currently working on in their LCA work. The bottom line is we have an entire presentation on that, from the estimates of improvement in lifetime for modified versus unmodified, and especially for highly modified now. So the bottom line is you get substantial enough improvement in overall life cycle of highly modified asphalt that it more than makes up for any additional GWP that you get from the addition of the polymer.
Thank you. Moving on, next question. Has HiMA been recycled using cold in place or hot in place recycling? Interesting question.
The simple answer there is that it hasn't been recycled at all, because basically nearly everything that has ever been paved with it is still in place. The only exception being on the NCAT test track, and there we would have to go back and ask what they have done with the millings. But that's an interesting question, and the simple answer is we don't know, because it really hasn't been done. We don't expect there to be any unusual issues with either cold in place or hot in place, but that's something that we still need to learn to understand.
Yeah, we're just not aware of it having been done with in-place recycling like that.
Okay. Perhaps maybe a follow-up question from my end. Maybe what some people may be thinking, since HiMA is such a strong material, can existing equipment actually come in and tear it out to be recycled?
Now, the simple answer for that is it's apparently not been a problem, because East Alabama Paving has milled up all of the HiMA sections that have ever been placed at the test track as part of their conventional normal cycles, and we've not heard any feedback that they had any issues whatsoever.
And by the way, that milling wasn't done because there were issues with performance. It was simply to remove material so they could prepare for the next section, where they would be building some other type of pavement section out there on the test track.
Thank you. And also, I wanted to just acknowledge and thank NCAT for their support and all the work that we've been doing together to promote this technology. It's been a really good partner for us. Next question, and that question actually came up quite often in many forms. It deals with storage stability. So is the storage stability an issue for the HiMA asphalt? What technologies are used for enhancing compatibility?
Storage stability from a separation standpoint isn't really an issue, and I think we've addressed that already. And again, what happens is that with a fully integrated polymer network within the binder, it almost can't separate. Now, another aspect of storage stability, though, is will there be changes in the material as it's being stored? And the answer is, as with other polymer modified binders, yes. The degree to which those changes take place depends somewhat upon the components, especially the bitumen that you're starting with and some of the chemistries there. But the main issue is with HiMA is that what you really want to do during production is you want to make the material and use it as quickly as possible. If you have extended storage, you want to try and lower the temperature. You do not need to raise the temperature of the storage tanks and the pumping temperature for handling the material. High temperatures, extended time can cause the viscosity to rise. That won't knock it out of specification, but it can cause issues for pumping and handling. Again, taking it, using it as you receive it, and if you have to store it for any amount of time, to store it at lower temperatures would be recommended.
Yes, and as we covered in the last segment of the video, Kraton supports development of the technology with our asphalt research centers. If you're located in the United States, we have one in Houston, Texas. If you're somewhere else, let's say in Europe, we have one in Amsterdam and we have one in Mumbai, India. And if you're running into any issues, we do always provide technical support in order to support the technology. So feel free to reach out to any of us. Again, our email addresses are here. You may not be able to read them, but certainly, let's see, certainly in the resource sheet that we will share with you at the end of this webinar, you'll find our email addresses. So, okay, well, quick question: Does HiMA have any impact to texture, micro or macro, which is important for skid resistance?
We actually have very good data on that, and then this is once again courtesy of NCAT, because NCAT measures all kinds of pavement performance and characteristics. Among the other things they measure is noise, skid resistance, so forth, and numerous HiMA pavements have been evaluated as just part of the rest of the track cycle. And essentially it has minimal change in surface texture, minimal change in noise. Now, if you move to then an open grade system, then there is substantial noise reduction, but nothing beyond what you'd expect for an open grade mix.
I guess there's two ways to look at that too. And one of them is, what affects the friction at the surface and so on. And that's going to be generated or controlled mostly by the aggregates, obviously, by the macro texture, which is just, can be measured with the sand patch test, and the micro texture of the aggregates, which is on the particles themselves in terms of providing the friction resistance that you have. The binder's not going to really affect that unless it's doing something to block it. And one thing about highly modified asphalt is the softening point of these binders is much higher than what's going to be experienced in the field. And so you're not going to see any bleeding occur. And so any loss of friction due to asphalt binder bleeding up to the surface is really not physically possible so much with highly modified asphalt. The other thing is that because the material is so much tougher and more elastic at high temperatures, you're not going to see a loss or much change in texture with dense graded mixtures over time as you might with some other materials. And also looking at open graded mixtures, as Bob was talking about, the enhanced resistance to raveling will provide for maintaining the qualities of that mixture for a longer period of time than with conventional materials.
Let me add one other point on that, which is an interesting opportunity. This is something that has been experimented with at NCAT, and that is to use a thin surfacing, microsurfacing, something like that, with highly modified asphalt with bauxite or other very hard, very skid-resistant minerals. And that allows you then to put on a very thin surfacing, but with a very skid-resistant aggregate. It's possibly the most cost-effective way to get such a skid-resistant aggregate into the surfacing of a pavement.
Bob, Gary, we talk in our video that HiMA technology on binder scale, asphalt binder, is basically 7.5% of this special SBS polymer. Can someone simply use a conventional SBS grade and put 7 to 8% and have a HiMA material? Is that doable?
Yes and no. You can formulate a material that will, you can formulate a binder that will have all of the properties that you want, with the exception of very high viscosity. So that creates then a challenge for construction. It's an additional problem though, because if you go to excessive temperatures in mixing and construction and compaction, then you get additional aging in the construction process. So because many states have limitations on plant operation temperatures, that is a limitation.
Mm-hmm. Thank you.
Yeah, and if you have an excessive viscosity of material, then that becomes a problem with handling the material both at possibly at a terminal, less so there, but more importantly at the hot mix plant, especially here in the United States, where mostly what we have are what are called drum mix plants, where you have a synchronization of the asphalt binder feed along with the aggregates. If the binder is extremely viscous, then that might affect the pumping systems and the ability to maintain the right level of introduction material, and thus affect the quality control of the mixture as it's being produced. HiMA, as we refer to it, is formulated to provide a viscosity that is not going to be anywhere near that range.
Okay.
And that's what distinguishes what we're talking about from using the more traditional polymers.
And at this point, thank you for the answer. I think at this point, it's again important to emphasize that the HiMA technology is not a proprietary technology, does not belong to Kraton. It is an open source, so to speak, technology, to which we provide a product that basically enables it. Did I capture that in the right way?
Mm-hmm.
A good question, and I think we answered it previously, but maybe to emphasize, how about the aging resistance of SBS and HiMA binders? Maybe more specifically, conventional PMA and HiMA binders aging.
Yeah, so there's no reason to believe that HiMA binders would age long-term any worse, certainly not. Perhaps even better aging resistance than conventional PMA. We have a grand total of 12 years of experience, and that's it so far with highly modified asphalt. So far, the aging behavior has been excellent with pavements that have been in place for 10 plus years. And again, to come back, the similar tests that have been done on pavements with conventional modified asphalt versus unmodified that are 20 years old show that the PMA is in better condition, both in terms of properties and retention of polymer, for that matter, than unmodified asphalt.
Thank you, Bob. And I think we often refer, especially in our website, if you go to www.pavewithkraton.com, there's a reference to a Swiss study which answers just the question that was asked.
That's the one I was referring to.
Yeah. You remember, Swiss study. The reference certainly is on our website, so please go there. Okay, another question. Is there any research regarding the use of HiMA on airport pavements?
Yes, indeed. And I think we covered that in one of the videos, that yes, there have been airport projects around the world. And again, if you just go to our website, there will be some examples of that. And it's an excellent opportunity for airport runways and taxiways because of the high shear resistance of the binder and of the mixtures. So it can tolerate the stress of landing gears, that first of all, the heavy weight of landing of airplanes, and then the stress, the shear stress for planes landing and taking off.
Yeah, and just to, again, going back to that question, I think the project that's been reported on the most was one done at an airport in Brazil, where HiMA was used in the service course for that. Something that comes to my mind on that, though, is that the FAA used to have a P402 specification, which was for a permeable friction course, which is no longer widely used. It's not published as part of their advisory circular anymore. And the reason for that is because open graded mixtures traditionally in the past had an issue with raveling, and foreign object debris or FOD is disastrous potentially where you're operating jet aircraft. Well, what we believe, based upon what we've seen with the research project that I mentioned before that was done at the Texas A&M Transportation Institute, is that with the enhanced resistance to raveling and just the generally tougher mixture that you have using highly modified asphalt is that you might be able to bring back those types of mixtures and for applications on airfield pavements, which would allow you to use those without having grooving, and you get some of the other benefits of open graded mixtures as far as the resistance or lack of hydroplaning, as well as the improvements to perhaps to the quality of runoff water that you see from open graded mixes, as opposed to just where you have a dense graded surface.
Thank you, Gary. Yeah, indeed. So there was the Viracopos airport, and there was the Prague airport that HiMA was used on. So we have a few examples on our website. Let me ask you this. If you find yourself in a position, let's say you're a pavement engineer in one of the states in the United States, or you basically are responsible for your assets and want to improve your pavement, what would be the way that you go about in order to implement HiMA, practical way?
What we have done in the past and what we always recommend is to get everyone involved on the same page and working on it at the same time. So as an agency, start off, find a project that you'd like to look at, see if you can do it. And the two options there, of course, are either finding an existing project and making a change order for a section of it, or a new project right from scratch. But in either case, talk to the contractor base, talk to the binder supplier base, get folks on board and get buy-in that people are interested and willing to work with you on these projects. That's in nearly every case, that has been where we have had the best and the easiest success in implementation.
Yeah, and just to add to that, as far as what we can offer on that, is that we will be happy to work with any agencies or with anyone who's interested to help develop a specification using their format. I know I've worked pretty closely with the Texas Department of Transportation to do that. And also, one thing that we would offer for initial projects is that if we can provide any in-place assistance, such as in pre-bid conferences, pre-construction meetings, that sort of thing, as HiMA is being introduced, we're happy to do that, just to make sure everybody understands what they're dealing with here, and that we assure that we give it the best chance for success.
And quite frankly, what we've found is that having one of us there, we don't necessarily really contribute anything, except that people have more of a comfort factor that if something looks a little different or something, there's somebody there to answer their questions.
Thank you. We just got one more question. Will this HiMA be effective in recycling HMA? That's a good question. So can HiMA be used to recycle pavements and can benefit that recycling process?
Well, we kind of addressed that before. There was a question about whether RAP could be used with highly modified asphalt, and indeed the answer is yes. The Florida DOT does not presently allow the use of RAP with highly modified asphalt, or high polymer as they refer to it. And the reason for that is because what they describe is they want to get the full impact of using a premium asphalt binder in all aspects. Now, what we've seen at NCAT and what we've seen in some other states is that typically we've seen, like at NCAT, up to around 20% used, like in the cracking group experiment that I described before, but up to 35% when developing a highly modified mixture, or a high modulus mixture. I'm sorry, I misspoke there. But there's no reason to think that you can't use highly modified asphalt in a mixture that contains reclaimed asphalt pavement.
And I would, and the other side of that is, in the future, milled highly modified asphalt, can it be used? Can it be recycled? Well, the simple answer there is we've been recycling modified asphalt pavements for 30 years in the United States. There's no indication that there's any negative aspects of that at all. And if anything, from the data that we've gotten on studies on the condition of milled pavements after cord pavements, after 20 years, one would expect, if anything, that it's going to be a better RAP than even conventional PMA, and certainly than unmodified asphalt pavement.
Right. And on our website, actually, there is a case study that deals with 40% recycled asphalt
Mhm.
using HiMA. So we encourage you to go there. Quick question, quick answer. Is HiMA used in the UK? Any plan? There's been a trial. We have a representative in the United Kingdom by the name of David Bell, and I will, Mr. Paraj, I will put you in contact with him. Next question, and we only have a few minutes, but we'll take those questions. For the asphalt binder producer, are there any measures you need to take when using this SBS, i.e. higher blend temperatures, longer curing times, or higher lower dosages of crosslinker? We're referring to 243.
Yeah. And that's going to be the same answer that we'll give you for pretty much any other polymer, that it's very much dependent on the asphalt. So that's something we're happy to work with you on. But yes, the polymers that we prefer to use, they can be compatibilized cross-linked thermally simply by using adequately high temperature. They work very well with the various sulfur donor cross-linkers that we're aware of, and there are a plethora of them. So fundamentally, there's not a fundamental difference between modification with the polymers that we recommend versus conventional SBS polymers.
And we all know that in our industry, asphalt binders or bitumen, depending where you are very, very complex and variable. Is there a possibility that HiMA may not work in a bitumen that's available in a certain place?
There will be cases where it's better or worse. We haven't found a bitumen where it is just absolutely unworkable at all.
Yeah.
Well, I think it winds up being kind of the same answer as you have if you're just looking at conventional polymer modified grades. And it might be fairly rare, but there are instances where some bitumen or asphalt binder sources just don't work well with SBS. I recall in my experience, we had one where you couldn't modify it with anything, and it just didn't work. But that was rare indeed. And again, that's something where we have capability of being able to work with our customers or with people, with bitumen suppliers, to help determine just the level of compatibility and which polymers work best under those conditions.
Thank you. And yes, exactly. We provide assistance. Let me ask you this question. Can HiMA be produced at the local PMB or local HMA plant, or does it need to be blended at the refinery or a terminal? If produced at the contractor plant, will he have to conduct testing that is required at the refinery or terminal? Big question.
There's nothing different about QC or QC requirements or QA with highly modified asphalt than with any other conventional PMA. So it's simply a matter, the difference is the amount of polymer that you're putting in. Everything else is at a fundamental level the same.
Okay.
Yeah, so you'll be getting it from your terminal or refinery more likely, unless you've got the ability to mill. And if you are doing that, then you'll be an asphalt binder supplier, and you'll need to qualify it that way.
I hate to say, but we're almost at 12:30 here in Houston, so we will need to pause it. But before you go, please wait a second. We will share with you through the screen a document that is sort of a summary of all the pertinent information that you need. So please download it or take a screenshot of your screen. And it has QR codes and links embedded in it, so it will take you right where you want to go. And I know that we haven't addressed all the questions that we wanted to address, but I promise you that within at most few days, we'll get back to all the questions and we will have them addressed and emailed back to you. With that, I would like to, first of all, thank you for attendance. It's been a pleasure. And thank Dr. Klatz and Mr. Gary Fitz for answering all the difficult questions that you had.
Well, thank you very much for joining us.
And thank you. Yes, we really enjoyed this. And thank you very much for your attention.
Absolutely. With that, I will mute ourselves. We'll leave the document here on the screen for a few moments. Please download it and have a great rest of your day.